Hi, just a quick follow-up video to my previous video, which is a response to the Batteriser monkey video where they tried to explain why power supplies are different to batteries, and it's actually quite a misleading video, and I went in detail and explained why they didn't actually measure it correctly and all sorts of stuff. So click here if you haven't seen that. I just wanted to do another quick follow-up video because one of my viewers, Andrew, sent in the real monkey. It's the same one that Batteriser used in their video. Thank you very much, Andrew. So I wanted to repeat their test where they showed the monkey working down to 2 volts on a power supply and why it didn't work with batteries measuring 1.25 volts per battery open circuit. Thought we'd reproduce it and see what we get. The answer's pretty obvious to anyone who knows about batteries. Let's go. Oh, by the way, this is Probes the monkey. So we'll call him Probes too. Let's go, Probes. So my test setup is very similar to before. I've got a BK Precision 8500 electronic load. I've got AA battery holder this time, and I've got big high current leads leading to there. Not that that matters, because this time I've actually got this extra sense wire tapped off here going around to the back of the BK Precision load. That's the sense input. So we're actually compensating for any loss whatsoever in any of those leads, and that's soldered directly onto the contact points here. The contact points also going over to the key site 34470A, so we can actually log the discharge curve. Now what I didn't show last time is that the BK Precision 8500 electronic load actually has a battery test mode. If I actually go in there, shift battery, for example, I can go, there we go. I can actually set a minimum voltage here of what I want this thing to cut out at. So I can set my constant current load, so it'll just continue to draw constant current from the battery until it hits whatever voltage we specify here, and then it'll automatically cut out. So the plan is to discharge 2 brand new batteries until they get to about 1.25 volts open circuit voltage, even though that's the wrong way to measure it and there's lots of traps in doing that. This is exactly what Batteriser did in this video. So I'll actually drain these things down using about half an amp, which is roughly what the monkey here, we'll call him Probes the monkey, what he actually takes, roughly on average. Okay, what I've done with this first battery here is I've discharged it to 1 volt at half an amp. So but it recovered to 1.38 volts. I wasn't sure because you're never sure what voltage it's actually going to recover to, because that's due to the ionic resistance of the battery, which is extremely dynamic, has to do with all sorts of factors. So yeah, I discharged it to 1 volt from fresh in the pack, and well, we only got to 1.38 recovered, and we actually extracted almost 1 amp hour. You'll notice I just turned this back on. It's not in battery mode again. Once again, we're still drawing half an amp constant current, and it was 1.38. I just switched it on then, and it's very quickly dropping. So it doesn't immediately drop back to 1 volt. And as I said, that ionic resistance of the battery, extremely dynamic chemistry at play inside this thing. But as you can see, it should very quickly in the scheme of things, because it actually took like 3 hours to discharge this thing or whatever to 1 volt, or 2.5 to 3 hours. So it should get back down to 1 volt pretty quickly. So what I'll do is I'll discharge it down to 0.9 volts and see if we can get around about that 1.25 volt open circuit voltage. Even though the open circuit voltage is not the right way to do it, hey, we want to reproduce what Batteriser did. And bingo, it's just finished discharging to 0.9 volts, and we sucked out an extra 0.44 amp hours. There we go, from going from 1 volt to down to 0.9 volts cut off after that constant discharge curve. And you can see it's jumped right back up to 1.2 volts. And this second battery's finished, and that took about 2.5 hours, I think, or thereabouts, and it's jumped back up to 1.2 volts. Actually, I'm not really happy with that at all. As you can see, they're recovering to 1.32 volts. I think I'm going to discharge these down to 0.85 volts. Let's go. So, shift, battery, 0.85, go. There we go. Okay, discharging the second battery, and we're going to log that one as well to 0.85 volts. And after that third discharge down to 0.85 volts, we drew a total of another 0.22 amp hours out of the thing. That's not too shabby. Geez, there can't be much juice left in it. Okay, discharging the second battery, and we're going to log that one as well to 0.85 volts. All right, I've now got 2 batteries that have been discharged 3 times. So really, there's hardly any juice left in these things. We've got 1.24 volts there, and we've got 1.27 volts there, so just over 2.5 volts, exactly the same open circuit voltage as Batteriser used. So let's stick them in the monkey. These are incredibly discharged batteries, but I think we'll find they'll still work because they've got still some energy left. Just a little bit. Should be enough to operate probes the monkey. Let's have a look. Here we go. No problems at all. They work just fine and dandy. Why is it so?
Watch. I'm pushing that finger. I'm pushing it. Did you see, Mr. Cork, that the stick did not tip? So I call your attention to the title of all my shows.
Why is it so?
Why is it so?
There you go. So why did the monkey under test work with my batteries at 1.25 volts each, or a total voltage of 2.5 volts open circuit, just like Batteriser's ones? It's very simple. It's the internal resistance of the battery. Everyone knows about this. It is hobby level stuff, as I've explained. My batteries, even though I brutally discharge them here, you got 3 discharge curves, most of the energy is gone. There's still enough energy left in there to operate this monkey. No problems at all. So the batteries that Batteriser used, even though they measured exactly the same open circuit as the batteries I used here, their ones were, there was no energy left in them. They must have discharged them down to bloody bugger all. No wonder it didn't work. And ironically, this test, the test that they used in their video for this monkey to prove that batteries are different to power supplies, as if anyone didn't know about internal resistance, ironically, the monkey is actually a very poor choice because this thing can extract virtually all the energy out of the batteries. It doesn't need the Batteriser. And the reason why they didn't actually put the dead batteries on the Batteriser and put them in the monkey, because it wouldn't have worked. It doesn't matter how magic your boost converter is, they're not going to work because there was no energy left in the batteries. Oh, goodness. How embarrassing. How can they put out a video like that? It's incredible. So this is why the Batteriser monkey video is not only wrong, but it's misleading, because it's making out that the open circuit voltage of the battery showing that they're 1.2 volts per cell implies that there's actually energy left in the battery, when in their case there is not. There is clearly no energy left in the battery. That's why people do not measure the open circuit voltage of the battery. It doesn't happen in industry because it's a very extremely poor indicator of whether or not there's energy left in this battery. Even Batteriser's own video showed that this monkey works down to 0.5 volts per cell. It extracts almost every drop of energy from the batteries.
That with a power supply, the monkey will operate, even when we bring the voltage down all the way to 0.9 volts. However, when using 2 batteries with a total voltage of 2.5 volts, the monkey will not operate.
Of course the monkey won't operate, because those batteries aren't 1.25 volts per cell when you stick them back up the monkey's butt, because you didn't do what I tried to explain in the previous video, that you must probe right here. And that is why using a power supply is exactly the same as using batteries when you actually measure the voltage where you should, which is right up the monkey's butt. And that's the trick which Batteriser don't seem to understand, is that one battery that measures 1.25 volts and another one that measures the same 1.25 volts open circuit, when you actually put them in a product, one cannot work at all because it just plummets because of the internal resistance, the chemistry. There's no energy left in the battery. But the other battery that measures exactly the same open circuit may still have some energy left in it due to how it was discharged and all sorts of complex, factors involved in the battery. The open circuit voltage doesn't tell you that. Everyone knows this, except Batteriser. So my batteries at 1.25 volts open circuit still had a little bit, not much, but a little bit of energy, enough to make this monkey work, because this monkey extracts practically all the energy from the battery. So the batteries they used clearly had zero energy left, because batteries can recover to a high terminal voltage. That's how ionic resistance and the chemistry inside a battery works. That's why you never, ever measure the open circuit voltage. And here's an example of this. In a previous video, you saw that I very slowly discharged at a constant power a couple of AAA batteries. This one was discharged at 100 milliwatts continuous, and I'll have to do a follow-up video showing the data for this. And this one was, but here's a quick look at the data. This one was discharged at 50 milliwatts, and this one here was discharged at 20 milliwatts, okay? So let's have a look at the voltage left in these batteries. Open circuit with no load, 1.2 volts, 1.15 volts. I discharged these things right down to zero, and they even oscillated down around zero. I left them there in continuous, practically shorting the things, and they still recovered to 1.2 volts. That's what the battery chemistry can do. But it doesn't mean there's much, if any, energy left in these. There is actually some due to the ionic resistance and the chemistry. There's a tiny little bit, maybe 1% of the energy still left to these completely discharged batteries. It could be less than 1%. So it might operate, a low power device for another hour or something like that. And that's what you can do, of course. You can stick these batteries into some low power device like this, for example, and it will still operate. So here we go. We'll measure that, 1.15 volts. There it is. We'll stick it in here and we'll find that this thing will still work. It's it's pretty dim, okay, but it still works. There's still a tiny amount of energy left in there. And let's measure the voltage in there. There we go. It's because this thing takes, absolutely nothing at all, really, except maybe when it beeps. There we go. Just see it drop when it beeped. So look, you can even still put them in something like this multimeter and it will still work. Look at that. It's not even showing low battery. That's because it hasn't dropped to a low enough voltage yet. Look, it's still, there you go, 2.32, okay? It'll even have just enough energy left to still operate the backlight like that, okay? However, it might be running at 5 milliamps or something, which is not much power at all. But if you measure the voltage in there, you'll see it's dropping, and it's going to continue to drop, and it's going to drop off pretty quickly. There's, you might get another half an hour's use out of this multimeter, out of the 300 odd hours that it normally operates. And no, don't jump to all the excitement that, that's a usage case for the Batteriser. Well, yeah, okay, it is, right? If your product doesn't extract all the, or most of the energy from the battery, but it's how much do you get out of it? An extra couple of %. And when you slap on the boost converter on this thing, it's going to be draining a lot more current than if you just put them in here like this. Because you've not only got the efficiency of the converter, but you've also got the increased current of the product because it's operating at 1.5 volts per cell instead of, down around 1 volt per cell or whatever these happen to be at the time. So just be very careful when you get all excited about a boost converter like the Batteriser. It's not magic. It's all to do with the amount of energy left in the battery. Physics 101. And this other battery I discharged at 20 millivolts. What happened to it? Well, let's take a look here. 0.11 volts. Why is it so? Take a look at it. It has leaked. Look. This is what can happen if you don't get the batteries out quick enough and you continue to drain them right down to zero. I might have left this one in for an extra, couple of hours or a day or something like that, to when compared to the other ones, and it leaked. And this is one of these Duracell Duralock ones that is not supposed to leak. They're supposed to have 10-year life, and there we go. Bloody leaked. Unbelievable. That's a danger of discharging batteries right down to zero and not getting them out quick enough. So here's the discharge curve that I actually got from this thing. And you can see that I did 3 discharges here, from here to this point, where then it recovered. And then as part of the ionic resistance of the battery, it recovers very quickly, and then it tapers off like that. And slowly, if you keep going, it actually recovers, probably up to 1.4 volts eventually, or maybe just a little bit under. And then I started the discharge again, and then, it jumps down straight away, but due to the ionic resistance of the battery, it starts to slowly discharge like that. It doesn't drop back to exactly this point because it's the dynamic electrochemistry of the battery, okay? You're not gaining any extra energy by doing that. The battery only has a fixed amount of energy in it, but that's why the voltage really is not telling the whole story there. So it gets down and down. So we extracted some more energy from here, and we turned it off, and then we extracted some more energy, 3 different periods, and the battery tester measured 0.797 amp hours, 0.44 amp hours, 0.22 amp hours, for a total of about 1.63 amp hours, 1630 milliamp hours. Now, just to clarify something here, amp hours or milliamp hours is not the true measure of battery capacity, because it's not taking into account the voltage. It's not power. The only true measure of energy in a battery, either energy used or energy remaining in a battery, is actually in watt hours. So that's why I've shown in previous videos how you can't just use the voltage. You've actually got to convert it to power, and it's the total integral under the power curve. So if you do constant power discharge, you can actually just read off the percentage directly from the x-axis here, but we're not doing constant power discharge, we're doing constant current discharge. Anyway, we extracted 1.63 amp hours out of the battery, but clearly these could still operate the Monkey, which is a fairly high drain device. So it still clearly had some energy left. It might have 5, I don't know, maybe even 10% left. And Duracell don't actually give you any data for the milliamp hour capacity in this case, but Energizer do. So Energizer's alkaline, just as an example here. Here we go, at our 500 milliamp constant current discharge, which you did on the Duracell. If you draw a line across there, it's around about 1400 milliamp hours, and we extracted actually 1630 from it. How were we able to do that? Well, because because this is continuous discharge, okay, just in one cycle. We did it in multiple cycles. You allowed it to recover, so we can actually get, just like you get increased capacity at lower currents, so lower average currents like this, so you don't necessarily have to discharge it at a lower current. You can still discharge it at 500 milliamps as we did here, here, and here, but because we let it rest for some time in between, this is not the true time, by the way, here and here. This is, that's only where I stopped doing the data, so it actually had more time to recover than that. So the average value is going to be better than this nominal 1400 in one continuous discharge. Anyway, that's just a quick little look at milliamp hour discharge. But yeah, like I said, there's probably not much left in this thing. The only way you can do it is to really time it in the Monkey itself. And I know what you're all saying, Dave, probe the Monkeys, but well, here it is, the MUT, the Monkey under test. I've probed in there these big probes here going to the banana plugs, which you can hook up to the battery or a power supply here. And then I've also got some leads. It was quite tricky, but I shoved them in the end of the probes right at the contact points right up in there. So I've set the power supply to 2 volts. If I turn it on, there we go. So 1 volt per cell, 2 volts total. As you can see, it's not dropping much at all because there's not much loss in these leads at all. So it's doing just fine. So now I'll do my 2 batteries, and the open circuit voltage of these batteries is 2.59 volts there, okay? So this is going to be a little bit tricky, so bear with me for a second. I've got to sort of use all of my hands. Hang on. I got to use my three free hands here, and there we go. And you can see it's dropped down to 1 volt, but it's not. There we go, 2 volts. Okay, so it's dropped from that 2.5 down to 2 volts because, well, there's not much energy left in the battery, so the ionic resistance drops that terminal voltage by a fair amount. And just like Batteriser, let's wind the voltage down. Here we go, 1.7 volts. Let's take it, at a volt. So that's half a volt per cell. The monkey is still working. This is an incredible probes. The monkey is absolutely amazing. But that's, he's pretty much dead there. The torque from the motor's just, can't do it. So that's why these ones still work, because there's enough energy left. It can keep the terminal voltage up above that 2 volts, up above, well, double what is required to operate the monkey. So what I'm going to do is discharge these things even more until I get to a point where they won't work in the monkey, and we'll see what happens. Even though the terminal voltage will be high, they will drop. When you actually plug them in here, it'll just plummet and it'll go under that 1 volt. You bet your life on it. And discharging to 0.6 volts, we were able, it's jumped back up to 1.11, we were able to extract another 0.31 amp hours. Beauty. All right, here we go. I've drained them a bit more and put them in here. There you go, 2.1 volts. Okay, so should be enough to operate probes the monkey, and I suspect we will get some juice out. Yes, I soldered some plugs onto there. Here we go. Let's have a look. He's getting real slow. Look, 1.48. But you put any resistance on there at all, and he's just gone. You hold him maybe up like that. The torque might be a bit more, and he's... you can see he's virtually dead. Okay, just drain a little bit more charge out of him by holding that. And, of course, the resistance of the motor in there. Look, he's gone. He's gone. Poor probes. Sorry, probes. But you can see the batteries that Batteriser must have used, even though they were measuring that terminal voltage. Okay, look, we're getting that voltage under load. 1 volt. So half a volt per cell, like he's dead. Okay, he's gone. There was no more energy, usable energy left in those batteries. Take it off, and here we go. It'll recover, and if you leave them there long enough, it'll probably recover up to quite a reasonable value. There we go. It's at 1.78 volts already and climbing. It'll probably get up to, once again, that 2.5 volts at 1.25 volts per cell, which Batteriser showed in their video. But you can see that it's just ridiculous, and they made out that measuring the voltage of the battery's open circuit was exactly the same as the power supply here, and it's not. It is completely different. Yes, batteries are different to power supplies, but you can see when we actually probe it in there, even with the power supply, it won't work. It's the terminal voltage of the battery that is dropping due to the electrochemistry, because there's no energy left in it. So a power supply is equivalent to using a battery when you probe it properly, like everyone in the bloody industry does. Except Batteriser. It's just unbelievable. So you can clearly see with no doubt whatsoever that a power supply is equivalent for determining the cutoff voltage of battery, because the cutoff voltage is probing right up the monkey's butt, right on the terminals. That's all that matters. Not the open circuit voltage of the battery. Of course, batteries are not the same as power supplies when you measure the damn thing's open circuit, because this doesn't have any electrochemistry. This thing does. All that matters is the cutoff voltage at the terminals there. So their very specific claim at the end of the video that me measuring the battery cutoff voltage with this is wrong and misleading at best. That was their claim. Here it is, right in the video.
To use a power supply to show a battery-operated device's cutoff voltage, ignoring the battery's internal resistance, is wrong and misleading at best.
And you can see that's total rubbish because they didn't probe it properly. Unbelievable. It's such a misleading video, this Batteriser one. It's completely busted. I don't know how I can bust it any more than that. So sorry that video was a lot longer than I was expecting, but as always I like to include detailed information of exactly what I'm doing because people are learning a lot from these videos and that's the intention. So there you go. I hope you found that video useful. If you did, please give it a big thumbs up on YouTube, and as always the link to the EEVblog forum down below for comments. Leave them on YouTube, blog site, all that sort of jazz. And I've got a whole bunch of other battery videos, not just on this Batteriser. I've had a whole bunch of videos for years. I've got like 10 battery videos or something crazy. So I'll link in the playlist, the YouTube playlist here, where you can go through and see them all. So just remember the moral of the story. Always probe the monkey's butt. Catch you next time.